Hello, ninth class students. I hope you all are doing well, taking care of all the COVID precautions which has to be considered. Now, FA2 is approaching in the coming week, 15th week that is. So the syllabus is chapter 3 and chapter 4. And now I am going to give you the revision videos attached to this particular chapters. Okay. So do watch them and make sure that you prepare well with these third and fourth chapter concepts, reflection of concepts and application of concepts majorly. So your major focus will be on reflection of concepts and application of concept questions. And in the third and fourth video, I'll be explaining the questions which you have to go through in the chapter 3 and chapter 4 for this FA2 preparations. Okay. 2 mark questions, again it will be a general questions, so be prepared with all these videos.
Refraction of light. You would have probably noticed that a spoon placed in a glass of water looks bent at the surface of water when viewed obliquely. The print on a page appears to be raised when the book is held behind a glass bottle filled with water. All these are the tricks of light. We shall explore how a light ray travels from one optical medium into another. You will need a glass of water, milk, pencil, a torch, aluminium foil, elastic band, needle. First, you need to prepare a point source of light. Observe how the torch is adapted as a point source of light. Here you've the point source of light. To give a cloudy effect for the glass of water, add a little milk to water. Darken the room. Shine the ray of light from the torch to the bottom of the glass. Observe the path of the ray of light. The path is crooked. This shows that a ray of light changes its direction of propagation as it travels from air to water. Similarly, a pencil which is partially dipped in water appears bent or broken to the observer. When a ray of light passes from air to water, its speed changes. Due to this, there is a change in direction of the ray. This change of direction suffered by a ray of light as it passes obliquely from one optical medium to another optical medium with different optical densities is known as refraction. Note that whenever a ray of light is incident on a surface separating two media, a small fraction of the light always gets reflected. Refraction can make an object appear to be in a different position. For the same reason, the part of the pencil which is submerged looks as if it has moved away from the part above water, and it appears fatter. Now, let's understand the phenomenon of refraction by studying the ray diagrams. Whenever a ray of light is traveling from a rarer medium to a denser medium, the refracted ray bends towards the normal. Here, IO is the incident ray, OR is the refracted ray, I is the angle of incidence, and R is the angle of refraction. In this case, angle I greater than angle R. If the ray of light is traveling from a denser medium to a rarer medium, the refracted ray bends away from the normal. Here, IO is the incident ray, OR is the refracted ray, I is the angle of incidence, and R is the angle of refraction. In this case, angle I less than angle R. For definitions, click on the labels. the ray of light striking the surface of separation of the media through which it is traveling is known as the incident ray. The perpendicular drawn to the surface of separation at the point of incidence is the angle which the incident ray makes with the normal at the point of incidence, the angle which the refracted ray makes with the normal at the point of the ray of light that has changed its direction at the surface of the ability to refract light is called the refractive index. Refractive index of a medium is equal to the ratio of the speed of light in vacuum or air to the speed of light in that particular medium. Refractive index is equal to speed of light in vacuum by speed of light in the medium. This ratio is always a constant for a given pair of media. It is represented by a Greek letter mu. Here are some of the effects of refraction. A straight pencil, PQ, when immersed obliquely in water, a portion of it appears to be shortened and raised up as P1, Q1 under the water. Let us understand this with the help of a ray diagram. Rays of light from the point Q are traveling from water to air. As the rays of light are traveling from a denser medium to a rarer medium, they bend away from the normal. After refraction at the surface, they appear to be coming from point Q1, which is true for each and every point of the part of the pencil which is immersed in the water. During spear fishing, the fisherman aims at the tail of the fish. When a fish in clear water is viewed from an angle, its image appears ahead of its actual position, as it is raised up due to refraction of light from water to air. Thus, if the fisherman aims at the head of the image of the fish, the spear will hit in front of the actual fish. However, if the aim is at the tail of the image, it is likely to hit on the head of actual fish. Go through the ray diagram to understand this. Twinkle, twinkle, little star. That's what we were taught. But do they really twinkle? No, stars do not twinkle. Let us now learn about why they appear to do so. The rays of light coming from the stars travel through the layers of air of varying densities. These rays get refracted continuously and they bend towards the normal as the refraction is from a rarer to a denser medium. The movements of air and convection currents causes a change in the density of the layers of air. As a result, the position of the image of the star goes on changing after every short interval. These different positions of the images formed at short intervals of time give the impression that the star is twinkling. At dusk or dawn, the sun appears to be larger than at noon. This is because when the sun is near the horizon, the rays of light coming from the sun have to pass through layers of air of increasing density. Due to continuous bending of light, the sun appears to be larger. At noon, the sun appears to be smaller than at dusk or dawn. This is because the rays of light that fall normally on the surface of the earth do not get refracted.
5 degrees. 10 degrees. 15 degrees. 20 degrees. 25 degrees. 35 degrees. 40 degrees. 45 degrees. 50 degrees. 55 degrees. 60 degrees. 65 degrees. 70 degrees. 75 degrees. 80 degrees.
'Effects of total internal reflection'. Total internal reflection is the reflection of light that occurs when it strikes an interface at an angle of incidence greater than the critical angle for the pair of media. Let us now discuss some of the effects of total internal reflection. Mirage in deserts and sparkling of diamonds are some of the effects of total internal reflection. Mirage in deserts. Mirage is an optical illusion seen very often in deserts, due to which an observer sees inverted images of distant objects. The observer thinks that the inverted image of the far-off object is the reflection of the object in water, although no water exists there. Let us see how this happens. In deserts, as the sand gets heated, the lower layer of the air becomes very hot, and the upper layers are comparatively cooler. A light ray coming downwards from any object passes through layers of air of gradually decreasing density. At each layer, refraction takes place and the light ray bends away from the normal. The angle of incidence continues to increase until at a certain layer the ray is incident at an angle greater than the critical angle of the air with respect to the next layer of air. At this interface, the light ray suffers total internal reflection and proceeds upwards from the rarer to the denser layer of air. The whole path of the ray is therefore concave as shown here. Due to this, the observer will see an inverted image of the object. The observer thinks that there is a pool of water from the formation of image. A similar phenomenon is observed on roads on hot summer days. It is due to total internal reflection that the surface of hot tar roads seem to be wet and shiny. Sparkling of diamonds. A diamond sparkles as the rays of light suffer total internal reflection at its various faces. Let us see how this happens. The critical angle for the ray of light traveling from diamond to air is very low, about 24 degrees. Therefore, most of the incident rays suffer total internal reflection. Moreover, the diamonds are usually cut with their faces in such a way that once a ray of light enters it, it suffers total internal reflections at various faces before it has any chance to emerge. Whenever the angle of incidence at any face is less than 24 degrees, the light comes out from it and the diamond appears to be bright. Thus, a ray of light on entering a cut diamond literally gets trapped within it for some time and causes it to sparkle. Optical fibers. Optical fibers are long thin strands of very pure glass about the diameter of a human hair. They are arranged in bundles called optical cables and are used to transmit light signals over long distances. A single optical fiber consists of 3 layers, namely core, cladding, and buffer coating. Core is the thin glass center of the fiber through which the light travels. Cladding is the outer optical material surrounding the core that reflects the light back into the core. Buffer coating is the plastic coating that protects the fiber from moisture and from any kind of external damage. The bundles are protected by the cable's outer covering called a jacket. How does an optical fiber transmit light? Transmission of light through an optical fiber is similar to the transmission of light through a hallway. When you have to illuminate a long straight hallway, you just have to point the beam straight down the hallway, as light rays always travel in a straight line. But to illuminate a hallway which is a winding one with multiple bends, you need to line the walls with mirrors and angle the beam so that it bounces from side to side all along the hallway. This is exactly what happens in an optical fiber. Optical fibers make use of total internal reflection to confine light within the core of the fiber. The core of an optic fiber has a higher refractive index than the cladding, and hence the light suffers total internal reflection. Although the cladding does not carry light, it is nevertheless an essential part of the fiber. The cladding is not just a mere covering. It keeps the value of the critical angle constant throughout the whole length of the fiber. Propagation of light in an optical fiber. Let a ray of light be incident on the fiber, making an angle theta c with the axis as shown here. It gets refracted into the fiber. Let the refracted ray make an angle theta I at the core and cladding interface. If theta I is greater than the critical angle theta c, then the ray suffers total internal reflection. So all the energy in the ray of light is reflected into the core and none escapes into the cladding. The ray then crosses to the other side of the core, and because the fiber is more or less straight, the ray will meet the cladding on the other side at an angle which again causes total internal reflection. The ray is then reflected across the core again in the same manner. In this way, the light zigzags its way along the fiber. Thus, the light gets transmitted to the end of the fiber. Because the cladding does not absorb any light from the core, the light wave can travel great distances. However, some of the light signal degrades within the fiber, mostly due to impurities in the glass. Terminology used in fiber optics. Here you can see a ray of light traveling from air of a refractive index μ0 into an optic fiber. The maximum angle of incidence in air, for which all the incident light is totally reflected at the interface of a pair of media having refractive indices μ1 and μ2, is called the angle of acceptance. Fiber attenuation. It is defined as the loss of light energy during its transmission through an optical fiber due to absorption by the impurities in the glass fiber. Applications of optical fibers. Optical fibers are used to transmit communication signals. In endoscope used to investigate interior organs which cannot be viewed directly, and in photometers. Refraction of light through a glass slab. Let us now perform an experiment and find out how light gets refracted when it is incident on a rectangular glass slab. Place the rectangular glass slab on a white sheet of paper fixed on a drawing board. Trace the boundary ABCD of the glass slab. Remove the glass slab. Draw IO to represent the incident ray. Draw the normal N1, N2 at the point of incidence O. Fix 2 pins on the incident ray IO. Place the glass slab within its boundary ABCD. Looking from the other side of the glass slab, fix 2 pins such that the feet of all the pins are in one straight line. Remove the glass slab and the pins. Mark the pin points P1, P2, P3 and P4. Join P3, P4 to represent the emergent ray O'(E). Join OO'. OO' is the refracted ray. Measure the angle of incidence, angle of refraction, and angle of emergence. Angle of incidence is greater than the angle of refraction, and the angle of incidence is equal to the angle of emergence. Extend O'(E) backwards. We observe that the emergent ray is parallel to the incident ray. The above experiment shows that when a ray of light is passing from air to glass, that is, from a rarer medium to a denser medium, the refracted ray bends towards the normal drawn at the point of incidence. The emergent ray O'(E) is the refracted ray emerging out of the glass slab. O'(E) is parallel to the incident ray. This means that the refracted ray has been displaced from its original path by a distance xy. This displacement is referred to as lateral displacement. We also observe that angle OO'(N1) is equal to angle R and angle E is equal to angle I. That is, angle E is greater than angle OO'(N1). This shows that a ray of light when traveling from a denser to a rarer medium